The situation involves a disagreement between an electrical inspector and an electrician regarding the grounding electrode conductor, or GEC, in an existing electrical installation. The inspector is raising concerns about the legality and safety of the existing GC connection, while the electrician believes they are not responsible for correcting pre-existing code violations. From the inspector's perspective, the grounding electrode conductor should be directly connected to the water main without passing through a changeover connector or meter. This configuration is crucial to ensure a reliable and low-resistance path for grounding. The inspector's insistence on disconnecting the changeover connector and establishing a new grounding electrode conductor connection to the water main aligns with the National Electrical Code, or NEC. The electrician's perspective is that they are not liable for rectifying existing code violations, especially since the grounding electrode conductor issue was not flagged during a prior inspection. The electrician might argue that the responsibility for addressing this concern now falls on the homeowner. Furthermore, the electrician might perceive the inspector as exceeding their authority by enforcing code compliance on an existing installation. Legally, and from a code standpoint, it's important to understand that the Massachusetts Electrical Code mandates that all electrical installations adhere to the NEC. An inspector possesses the authority to enforce this code and issue violations when necessary. However, a generally accepted principle is that existing installations are typically not required to be upgraded to meet the latest code standards, unless they present a clear and present safety hazard. Several solutions can be considered to resolve this conflict. Firstly, the homeowner could engage the electrician to rectify the grounding electrode conductor connection in accordance with the inspector's requirements. Secondly, the electrician could proceed to disconnect the existing grounding electrode conductor and connect, or BND, to the existing grounding electrode conductor, as specifically requested by the inspector. Thirdly, the electrician could attempt to open a dialogue with the inspector to discuss the matter further. The goal will be to determine if a compromise can be reached. For instance, it might be possible to allow the existing grounding electrode conductor to remain in place, provided it successfully passes a resistance test. Ultimately, the homeowner and the electrician should seek legal counsel to fully understand their respective rights and responsibilities in this situation. The grounding electrode conductor is a critical component of the electrical system. It provides a path for fault current to return to the source, helping to trip the circuit breaker and clear the fault. A properly installed grounding electrode conductor helps to minimize the risk of electrical shock and fire. The National Electrical Code, specifically Article 250, provides detailed requirements for grounding and bonding. Section 250.24 covers grounding service supplied alternating current systems. This section outlines requirements for grounding conductors, connection points, and the use of grounding electrodes. Section 250.50 and subsequent sections address grounding electrode systems and the specific requirements for various types of grounding electrodes, such as metal water pipes, ground rings, and concrete encased electrodes. Section 250.52 details the types of grounding electrodes that are permitted, including metal underground water pipes, metal frames of buildings, concrete encased electrodes, ground rings, and rod and pipe electrodes. The code specifies requirements for the size, installation, and connection of these electrodes. Section 250.53 provides additional details on the installation of grounding electrodes, including requirements for depth, spacing, and protection from damage. Section 250.64 covers the grounding electrode conductor installation. This section outlines requirements for the size, material, and route of the grounding electrode conductor, as well as requirements for its connection to the grounding electrode and the service equipment. Section 250.68 specifies the requirements for the connection to grounding electrodes. It details how the grounding electrode conductor should be connected to various types of grounding electrodes, ensuring a secure and effective connection. Section 250.70 covers the methods of grounding conductor connection to electrodes. It provides guidance on the types of connectors and methods that are suitable for connecting grounding conductors to electrodes, ensuring a reliable and corrosion-resistant connection. The size of the grounding electrode conductor is determined by NEC Table 250.66, which is based on the size of the ungrounded service conductors. For example, if the service entrance conductors are 2/0 AWG copper, the grounding electrode conductor should be at least 4 AWG copper. The connection of the grounding electrode conductor to the water pipe must be made within 5 feet of the point where the water pipe enters the building and must be supplemented by an additional electrode, such as a ground rod or ground ring. The water meter must be jumpered with a bonding jumper to ensure continuity of the grounding path. A changeover connector in the grounding electrode conductor is not permitted by the NEC. The grounding electrode conductor must be continuous and unbroken. The purpose of grounding is to provide a low impedance path for fault current to return to the source, tripping the overcurrent protection device, circuit breaker, or fuse and clearing the fault. Without proper grounding, a fault can cause a dangerous voltage to appear on metal parts of equipment, creating a shock hazard. Grounding also helps to stabilize voltage during normal operation, reducing electrical noise and improving the performance of sensitive electronic equipment. The inspector's concern about the existing grounding electrode conductor configuration is valid, as it does not meet the requirements of the NEC. The changeover connector and the lack of a jumper around the water meter create a potential break in the grounding path, increasing the risk of electrical shock. The electrician's argument that they are not responsible for correcting existing code violations is a common one. However, when an electrician makes any modification to an existing electrical system, they become responsible for ensuring that the entire system meets the current code requirements. This is especially true for safety-critical components like grounding. The legal and code implications of this situation are complex. While it is true that the existing installations are not always required to be brought up to current code, the inspector has the authority to require corrections if the existing installation poses a safety hazard. In this case, the inspector believes that the improper grounding electrode conductor configuration creates a safety hazard, and they are justified in requiring it to be corrected. There are several possible solutions to this problem. The homeowner could hire the electrician to correct the grounding electrode conductor configuration to meet the current code requirement. This would involve removing the changeover connector, installing a jumper around the water meter, and ensuring that the grounding electrode conductor is properly sized and connected to the grounding electrodes. Alternatively, the electrician could contact the inspector and discuss the issue further. It may be possible to reach a compromise that addresses the inspector's concerns while minimizing the cost and disruption to the homeowner. For example, the electrician could perform a ground resistance test to verify that the existing grounding electrode conductor provides an adequate grounding path. If the test results are satisfactory, the inspector may be willing to allow the existing configuration to remain in place. Ultimately, the decision of how to resolve this issue will depend on the specific circumstances and the willingness of the homeowner, electrician, and inspector to work together to find a solution that meets the needs of all parties. It's important to remember that the primary goal of electrical codes is to ensure the safety of people and property. While code compliance can sometimes be costly and inconvenient, it is essential to protecting against electrical hazards. The grounding electrode conductor GC plays a vital role in electrical safety by providing a path for fault current to return to the source, tripping the circuit breaker and clearing the fault. A properly installed grounding electrode conductor helps to minimize the risk of electrical shock and fire. A ground ring is a type of grounding electrode that consists of a bare copper conductor that is buried in the earth in a circular or loop configuration. The ground ring encircles a building or structure and provides a low impedance path for ground fault current. The NEC requires that ground rings be buried at a depth of at least 30 inches below the surface of the earth. The conductor must be at least 2 American wire gauge copper. A concrete encased electrode, often referred to as a UFA ground, consists of at least 20 feet of bare copper conductor that is encased in concrete. The conductor must be at least 4 American wire gauge. The concrete must be in direct contact with the earth. UFA grounds are typically installed in the footings or foundation of a building or structure. Rod and pipe electrodes are the most common type of grounding electrode. They consist of a metal rod or pipe that is driven into the earth. The NEC requires that rod and pipe electrodes be at least 8 feet in length and be driven into the earth to a depth of at least 8 feet. Rod electrodes must be at least 5/8 inch in diameter, while pipe electrodes must be at least 3/4 inch in diameter. The NEC specifies requirements for the size, material, and installation of the bonding jumper. The bonding jumper must be sized according to NEC Table 250.102 cone. The material of the bonding jumper must be copper or other corrosion-resistant metal. The bonding jumper must be installed in a manner that provides a low impedance path for fault current. The bonding jumper must be protected from physical damage. The main bonding jumper is the connection between the grounded conductor and the equipment grounding conductor at the service equipment. The main bonding jumper provides a path for fault current to return to the source, tripping the overcurrent protection device and clearing the fault. The equipment grounding conductor (EGC) is a conductor that connects the non-current carrying metal parts of equipment to the grounding system. The equipment grounding conductor provides a path for fault current to return to the source, tripping the overcurrent protection device and clearing the fault. The equipment grounding conductor must be sized according to NEC Table 250.122. The equipment grounding conductor must be installed in the same raceway or cable as the circuit conductors. The equipment grounding conductor must be connected to the equipment grounding terminal of the equipment. The grounding electrode system must comply with NEC sections 250.50 through 250.70. The grounding electrode system must be effective in providing a low impedance path for fault current. The grounding electrode system must be properly maintained. The grounding electrode system must be inspected periodically. The grounding electrode system must be tested periodically. The grounding electrode system must be repaired or replaced as necessary. The NEC specifies requirements for the size, material, and installation of the grounding electrode conductor. The grounding electrode conductor must be sized according to NEC Table 250.66. The material of the grounding electrode conductor must be copper or aluminum. The grounding electrode conductor must be installed in a manner that provides a low impedance path for fault current. The grounding electrode conductor must be protected from physical damage. The grounding electrode conductor must be continuous and unbroken. The inspector's request to disconnect the changeover connector and run a new grounding electrode conductor to the water main is in line with the NEC National Electrical Code. The inspector may be concerned about the legality and safety of the existing ground electrode conductor GEC connection. The GEC should be directly connected to the water main without passing through a changeover connector or meter. This ensures a reliable and low resistance path for grounding. The electrician argues that they are not responsible for correcting existing code violations. They contend that the GEC issue was not detected during the previous inspection, and it is now the homeowner's responsibility to address it. They also believe that the inspector is overstepping their authority by demanding code compliance on an existing installation. Massachusetts Electrical Code requires that all electrical installations comply with the NEC. The inspector has the authority to enforce the code and issue violations. However, it is generally accepted that existing installations are not required to be brought up to current code standards unless they pose a safety hazard. The homeowner could hire the electrician to correct the GEC connection. The electrician could disconnect the existing GEC and connect a burndy to the existing GEC as requested by the inspector. The electrician could contact the inspector and discuss the issue further to determine if a compromise can be reached, such as allowing the existing GEC to remain if it passes a resistance test. Ultimately, the homeowner and electrician should consult with legal counsel to determine their rights and responsibilities. The NEC, or National Electrical Code, provides the standards for safe electrical installations. Inspectors use it to ensure compliance, safeguarding people and property from electrical hazards.